In Part 2 of Lecture 8, we will discuss organizing memory. In organizing memory, there are several different models that we will choose to look at. The simplest model is simply having no restrictions on memory use. This is, for all practical purposes, a bare machine. No operating systems, no services, nothing but user program. This is rarely used because programmers do not like having to write everything themselves, including their own device drivers. The only time it is used at all is in real-time systems where users are extremely concerned with execution speed and are willing to do everything it takes to speed up execution. Even then, as processors get continually faster, it is rarely used. Most systems, however, do have operating systems, and we want to ensure that user programs do not corrupt the system code or data. And it's not just a matter of trust. Most potential problems are due to accidental intrusions, not deliberate sabotage attempts. That means that we need to partition memory into two distinct regions, one for the operating system and one for user programs. We want to place the operating system at either the high end or low end of memory. Which end we use is only important because it must include the interrupt vector, an array containing the addresses at which the various operating system interrupt handling routines are located. The simplest practical memory management scheme involves a single partition for user processes separated from the operating system. The address available to a user process is kept in a fence register. User processes are given no access to physical addresses below the fence register. The fence register is also a base register for user process addresses. We'll take a more detailed look at this in a moment. Before we look at how physical addresses are determined in this scheme, let's answer a more immediate question. Why store the starting address of user memory in a register? Why not hardwire the value? That limits our ability to change the operating system. We would be forced to stick within very strict limitations. If that value is too small, we leave no room for expansion. It's possible then that the operating system might not fit entirely in the memory allotted for it. And if it's too big, we tie up memory that the operating system might not need, but that the user may need. Also, we are allowing the operating system to load rarely used components only if they're needed. They can be loaded following the resident portions of the operating system. The fence register is then adjusted accordingly, and then a user program is loaded a little farther down in memory than it might have been if not for the additional component. The slide shows how this looks in diagram form, assuming that this component is a rarely used device driver. Any memory management scheme requires the support of the hardware. We will assume that in most cases there is an upper limit, some address above which the process cannot access. This may be because that address is past the physical limits of memory, or because the system is reserving that area of memory for another process. In either case, we need to store the address above which the process cannot access in a limit register. Any logical address beyond this point will result in an addressing error. It is also important to note that the limit register contains a logical address, not a physical address. If the address is valid, then it is added to the contents of the relocation register, which holds the base address for the program. This results in a physical address that is used in accessing memory. The relocation register does not have to be a special register. It can be a regular register that is used for this purpose as well, or it can be one of several general purpose registers, and the instruction can indicate which register it is. The last method was used by the IBM 360 and 370 families of mainframes. So far, we have limited our discussion to situations where only one process is resident in memory. While there have been many computer systems that used this scheme, such as earlier versions of Unix, it slows down performance and limits throughput because every process switch requires swapping. We can improve performance by keeping more than one process resident in memory at a time. There are two different ways in which we can do this if processes are going to be in contiguous memory allocations, where the area of memory that they have is adjacent without any discontinuous areas. We can assume that there will be some fixed maximum number of processes. We partition memory into a predetermined set of regions where a process is loaded. The only problem is that this requires that the processes be able to fit in the available regions of memory. The only alternative is that we allow the number of resident processes to vary. Obviously, this makes the job more complicated. We have to be able to accommodate processes of different sizes in different numbers. As we will see, this is more useful, but also more difficult to manage. The first method is called MFT, multiprogramming with a fixed number of tasks. It assumes that we will have up to n processes resident in memory at a time. Memory is divided into n partitions of fixed size. These partitions do not have to be equal in size. In fact, that may not be the best way of partitioning user memory. MFT was used in IBM's OS 360. It was useful to some extent in batch systems, but is no longer used. MVT stands for multiprogramming with a variable number of tasks. It assumes that there is no specific number of processes that will be resident at one time. The actual number will depend on the size of available memory and the memory requirements of the processes in memory and that will be loaded into memory. It now becomes the job of the operating system to keep track of what portions of memory are in use, what parts of memory are available, and which processes are likely to fit in there. Imagine for a moment that the computer has just been booted and all you have in memory right now is the operating system. Then the operating system gets a request to load process 1. The first step is to load the process's code into memory, and that requires allocating storage for it. What you see in the left diagram is memory before the process's memory is allocated. The middle diagram shows memory after the allocation. Now, let's say that we have another process start. It will also need to have memory allocated, and we see what memory is in use on the right. Let's complicate matters a little and say that process 3 gets a block of memory allocated and then process 2 finishes. We have a free block of 4 megabytes available. This can now be allocated for another process or processes. There is no fixed requirement that this block be allocated in its entirety to one process. How we allocate it depends on what the needs of the resident processes and loading processes are. Let's say that the new process being loaded needs 5 megabytes. The computer has at least that much available memory. But it's not one contiguous block. It's broken into 2 discontiguous blocks separated by the block of memory that process 3 is using. This means that we can't load process 4 despite the fact that we have enough memory, all because it's in 2 separate blocks. This kind of problem is called fragmentation. It refers to cases where the individual blocks are too small to be of use, even though the total is sufficient for our purposes. We will look at the potential solution to fragmentation in a minute. But first, let's take a look at some strategies for allocating memory. Fragmentation and how to avoid it will be an issue in deciding which strategy is most suitable. There are 3 different criteria that we can use in selecting an available block of memory. We can use the first fit, the best fit, or the worst fit. In the first fit, the operating system loads the program into the first block of memory large enough to hold it. The strategy assumes that there is no real advantage in placing our program in any particular gap in memory. As a result, we place it in the first available gap which we can find the most quickly. Unfortunately, this may mean using a gap that might be a perfect fit for another process, and that process may not fit into any of the other available gaps. This makes first fit a less than ideal strategy. If we are looking to match a process's memory requirements to the available space, the best fit strategy would be a much better choice. We search for the gap which comes closest to our requirements that is also larger than our requirement or equal to it in size. After all, a gap which is smaller than our requirements does us no good. The only problem is that it is unlikely that we will be able to make use of any gap left over after allocating storage for this process. An alternative strategy is the worst fit strategy. It assumes that it is best to look for the gap that leaves the most leftover space, presumably because we will have more luck in fitting a process in there. While this third strategy may make it easier to use memory efficiently, it will minimize fragmentation but not eliminate it. But as we will see shortly, there is a way to eliminate a great deal of fragmentation. When blocks of memory are allocated to a process, they are usually in units of a certain size, either 500 bytes at a time, or a kilobyte at a time, or possibly larger. To allocate smaller units of memory increases the cost of keeping track of it. The end result is that if your system allocates a kilobyte at a time, and your process needs 2050 bytes, 3 kilobytes will be allocated, which is 1022 bytes more than you needed, simply because it cannot allocate a more exact amount. And the extra bytes will be wasted because your process has them and is not going to use them, and no other process can have them until your process gives up its 2050 bytes. This is an example of internal fragmentation, where space within an allocation goes unused because it is too small to be allocated on its own. If there are gaps between allocated blocks of memory that are too small to be used by any new process seeking an allocation, this would be external fragmentation. What can we do to minimize or eliminate fragmentation? Well, there is little we can do about internal fragmentation other than keep the size of the allocation unit as small as practical. But we will see that there is something we can do about external fragmentation, though there is a price to be paid. We can eliminate external fragmentation by compacting memory, moving processes in memory so that allocated blocks of memory have no unallocated blocks between them. In this way, user memory is divided into an allocated area and a free area. This free area is large enough to accommodate any new process being loaded into memory, because we have combined all the small areas of available memory into one large one. The first question that comes to mind is, where in memory do we put the free space? We can move all the processes as far toward the low end of memory as possible, or move the processes that require moving to the high end of memory. It really is not important as long as we consolidate all the free memory into one large contiguous section, so we can allocate it and partition however we see fit.